Good day, viewers and listeners. I am Ms. Cham, and we are here to continue with our lesson, which was based on uniform circular motion. But before we start, we'll take a recap of what we did before. Now, if you remember, we dealt with the definition of UCM, that is uniform circular motion, and the examples. We also talked about the variables such as angular displacement, linear or angular velocity, and that of angular acceleration. And I also showed you how these equations are related to one another. We're going to solve our first problem, and then from there, the lesson continues. Is that understood? Good. The problem we have on the board reads, a body moves around a circle and covers a distance of 50 meters in 8 seconds. If the radius of the circle is 15 centimeters, determine the body's A, linear velocity, and B, angular velocity. Now, if you look at it, we related V and omega R's. V is omega R. That is what we did last time when we met. And here the problem says we determine, the first part says the linear velocity V, and the second part says the omega, which is angular velocity, if the object covers a distance s of 50 meters in time t equals to 8 seconds, and then the radius of the circle is given as 15 centimeters, which is 15 times 10 to the power minus 2 meters, which is also 0.15 meters. Good. Now we know that V is omega all over R, but then omega is not known, R is known. Again, we can solve for omega. We know omega to be theta all over T, but then theta again is S all over R. So what's the value of S given? It's 50 divided by the radius, which is 0.15. So let's point that into our equation and see. We know the angular displacement theta to be 50 divided by 0.15, and that is 333.33 radians. That is it. And then to solve for omega, we just divide that by the time taken. We know omega to be theta all over R, theta all over T, and theta is 333.33 radians divided by the time, which is 8 seconds, and that gives us 41.67 rads per second. Good. So that is the B part of the equation, and the A part will be V equals to omega times R. Omega is 41.67 and the radius is 0.15. So this multiplied gives us 6.25 meters per second. Yeah, that's question 1A and B. Now question 2 says, the rim of a wheel of a machine starts from rest and attains an angular velocity of 12.4 rads per second after 50 seconds. Calculate the angular acceleration, which is called question mark here because we don't know what it is. Good. But if you recall, we know that the angular acceleration is given as the rate of change of omega, which is delta omega all over delta t, and that should be omega minus omega naught all over t minus t naught. Therefore, alpha will be omega, which is 12.4 minus omega naught, which is 0 since it started at rest, all over the time t 50 minus 0. So that gives us 12.4 divided by 50, and that should be 0.248 rads per second squared. Is that understood? Good. I think that's okay for today. That's the problems are okay for today. We move on to something we called acceleration. Now remember, I told you if an object moves with a change in velocity, it accelerates. But if the velocity is constant, then the acceleration will be 0. But if you recall from when we started, I told you that when an object moves in a circular path, two things occurs. The magnitude of the velocity will be the same, but then the direction of the velocity changes from one point to another. That is the velocity. In other words, the speed will be the same, but then the velocity changes. And the speed talks about the magnitude of the velocity. Is that clear? So, and what else we know was that the radius of the circle will also be constant. It wouldn't change. Is that understood? Now, when an object moves in a circle, this is what happens. It accelerates, and the direction of the acceleration will be towards the center of rotation. This is what happens. Let's label this point A, B, C, and D. When the object is at point A, what happens to the magnitude of the velocity? It will be the same. It will not change, but the direction will be somewhere around that end. But then the acceleration will always be directed towards the center of rotation, towards the center of rotation or axis of rotation. When the object is at this point, the acceleration will be, let me use a different color chalk. The acceleration will be towards the center of rotation, but then the velocity will be vertically downwards. Is that understood? This is A and this is V. This is also A, this is also V. When the object is here, the velocity turns to the left, and then the acceleration will be towards the center of rotation. Is that understood? Now, this is what you have to understand. Though the magnitude of the velocity is constant, but then the direction changes. This is why it is possible for an object to accelerate, even though its velocity is changing, but then the magnitude of the acceleration will be constant. Have I communicated? And the direction of this acceleration will always point towards the center of rotation, as indicated on my diagram. Is that clear? Good. We move on. And in essence, the other thing you need to understand is that when an object moves in a circle, the total acceleration is as a combination of two. The radial acceleration, which we call the centripetal acceleration, and also the tangential acceleration. The tangential acceleration is as a result of the angular velocity. That is, this is A tangential, and A radial will always point towards the center of rotation. Is that clear? Now, these two accelerations will be obtained, and when added, it gives the total acceleration of the body. Is that understood? Now, look at the other part. It says, in essence, the total acceleration of the body performing rotational or circular motion is just the sum of the tangential and radial accelerations. This can be obtained by differentiating the equation which relates angular and linear velocities with respect to time. And I will just draw your mind to that part. We related V and omega, and that was V is equivalent to omega r. This velocity is very, very important. If we differentiate this velocity with respect to time, the total acceleration will be obtained. And then that simply tells us, I know some of you have not done differentiation, but it is not tough. If you're following my lesson, you'll be able to differentiate this. And the method of differentiation we will use is the product rule. And when we use the product rule, we are using the product rule because the other side of the equation deals with a product. That is omega times r. That makes it a product. So if you have to differentiate this, we will use the product rule. And in using the product rule, you will keep one as a constant and differentiate the other with respect to time. Is that clear? Then you join the two by an addition sign. Then the one that was differentiated with respect to time will be kept as a constant, and the constant, the first one you kept as a constant will now be differentiated with respect to time. That is all about the product rule. Is that understood? Good. Now let's go on and see. We are told V is equivalent to omega r, and we have to differentiate this with respect to time. So this will be dv all over dt is equivalent to d omega r all over dt. But omega r is a product. We cannot just differentiate it once. We will use the product rule. And that gives us dv all over dt is equivalent to, which one are we keeping as a constant? Let's keep omega as our constant, and that will be omega. It will not be differentiated at this instant. Omega, and we differentiate r with respect to time, and that will be dr all over dt plus, which one was differentiated? It was r. So then r becomes our new constant. R becomes our new constant. Then we differentiate omega with respect to time. This is in order to obtain the total acceleration. Remember, I told you the total acceleration, AT, is equivalent to A tangential plus AC. Is that clear? Now let's see what happens here. If you differentiate velocity with respect to time, you obviously obtain acceleration, and this will be A capital T as the total acceleration, which is equivalent to, we are keeping this as a constant, so we bring it down. Displacement over time gives us what? Velocity. Displacement over time will always be velocity. Plus, r is a constant, we bring it down. If we differentiate omega with respect to time, what will we have? Omega over time gives us what? The angular acceleration. So this is nothing new. It is very simple. Let me go back to that point again. We are differentiating velocity with respect to time. And this is done on both sides of the equation. So if we divide velocity with time, what do we have? It's acceleration, and that is the total acceleration. Now, since this is a product, we will apply the product rule in differentiating it. And that means one must be kept as a constant, whilst you differentiate the other with respect to time. The one that was your constant will now be differentiated, and the one that you differentiated before will now act as your new constant. Is that understood? Good. And that will be omega, which is our constant. We differentiate displacement with time. If you divide displacement with time, you have velocity. And this is not differentiated omega, so we bring it down. Have I communicated? Good. And r will now be our constant. We differentiate omega with respect to time. Change in omega all over change in time is always alpha, which we call the angular acceleration. This is why I obtained something like AT, which is equivalent to omega v plus RT. If you look at the previous slide, I told you that the total acceleration of a rotating body is just the sum of the radial or centripetal acceleration plus the tangential acceleration. So omega v gives us the centripetal acceleration, whereas r times t or r times alpha gives us the tangential acceleration. Is that understood? Good. We move on. Good. Just follow the slides. Good. That's the diagram that I've drawn here. Now, since AC is what causes the centripetal acceleration, we will just pick it aside. We know AC to be equivalent to omega v. A tangential is equivalent to r alpha, and A total is equivalent to AC plus AT. This is very important. Is that understood? Now, to obtain the magnitude of centripetal acceleration, we will just focus our attention to omega v. And this gives us the magnitude of the centripetal acceleration. Remember, we talked about the direction, and I told you the direction will always be radially inward, or in other words, it will always point towards the center of rotation. That is the centripetal acceleration, and others can call it the radial acceleration. We're still referring to the same thing. That's the direction, and the magnitude is obtained by using AC equals to omega v. Is that clear? We know that omega, where omega is v over r. Therefore, the magnitude of AC will be omega. In place of omega, what will I write? V all over r times v. So AC will be v times v is v squared all over r. This gives us the magnitude. of the centripetal force, and the direction is always towards the center of rotation. You've seen the derivation there. The direction of centripetal acceleration will always point towards the center of rotation. Is that understood? And the magnitude is v squared all over r, and that is how it is obtained. Now we have a problem on the board, and it reads, is it possible for an object moving with a constant speed to accelerate? Explain your answer. Option A says no. If the speed is constant, then the acceleration is 0. And option B says no, an object can only accelerate if there is a net force acting on it. And C, yes, although the speed is constant, the direction of the velocity can be changing. I think C is the correct option there, because if you look at what I drew before, I told you the magnitude of the velocity is always the same, but then the direction changes from one point to another. Like if you recall, when the object was at the top, the direction of the velocity was to the right. When the object was at the bottom, the direction was to the left, but then the magnitudes were the same all throughout. Is that clear? So the correct option to that problem is letter C. We move on to the second problem, and it reads, consider a particle moving with constant speed such that its acceleration of constant magnitude is always perpendicular to its velocity. Now what will happen? A says the object is moving in a straight line. Is that true? No. B says the object is moving in a circle. Yeah, that should be the answer, and that's the answer. When an object moves, in a circle, the velocity would always be perpendicular to the acceleration. This is because the acceleration will always tend to be directed towards the center of rotation. That is the direction of radial acceleration, but then the velocity will be, the direction will changes. And if you trace the diagram, you will notice that in both cases, or in any case, the velocity will always be perpendicular to the acceleration. Have I communicated? Good. Letter C. An object moves, not letter C, problem 3. An object moves in a circular path at a constant speed. Compare the direction of the object's velocity and acceleration vectors. A, both vectors point in the same direction, I don't know. B, the vectors point in opposite directions. And C, the vectors are perpendicular. And D says the question is meaningless since the acceleration is 0. D is wrong because the acceleration is not 0, and I've explained that the acceleration will not be 0. This is because the velocity is changing. The direction of the velocity changes, though the magnitude is constant. So as a result, the acceleration cannot be 0. And then the correct option to this problem is letter C. And you can refer to my diagram here. You will notice that the velocity will always be perpendicular to the acceleration, as shown on the diagram. Okay, now look at the last one. It says two cars go around the same circle at the same speed. Good. The first car is closer to the inside of the circle. Which of the following is true about their centripetal accelerations? Now let me give you a hint before you answer this question. If you look at my derivation, we obtain something like the centripetal acceleration AC is giving us v squared all over r. And from this equation, we can simply say the centripetal acceleration varies directly. It is directly proportional to v squared, and then AC varies indirectly or is inversely proportional to R. That is, AC is equivalent to something all over R. And this tells us that if that something, which is the velocity, is kept as a constant and the radius of the circle is reduced, if the radius is reduced, what will happen to the acceleration? It will be increased because they are inversely proportional to each other. But then if the radius is, if v is constant and the radius is increased, what will happen to the acceleration? It will be reduced. Is that understood? But then looking at this scenario, you are told that one of the cars was very close to the circle, but then their velocities were the same. Now, which of them will finish the race? You answer the problem now. I will read out the options. A, both cars have the same centripetal motion since they both have the same velocity. But what happens to their radius? Is it the same? No. Then letter B says, the centripetal acceleration of the first car is greater since its radius is smaller. Well, you can choose that if you want, but then use the mathematics behind, the reasoning behind. If the, how to call it, if the radius is h, what will happen to the acceleration? It should be lower, isn't it? But then if the radius is smaller, then the acceleration must be bigger. Just use that concept and answer this problem. We move on to our next slide, and that one talks about period, frequency, and rotational velocity. Okay, now these are some terms that we need to understand, and they are the period. When we talk about period, it just tells us the time taken for an object to go around a circular path. The time taken to make a particular revolution is what we call period. And mathematically, it is expressed as capital T. The period is denoted as capital T, and it is mathematically expressed as the time taken to cover a number of oscillations, or number of revolutions. Good. And this simply tells us T equals to small t, that's the time taken to go around a circular path, all over the number of revolutions n. N does not have a unit because it is just counting. It is indicating the number of times an individual has gone around a circle. So t, small t, is measured in seconds, and n has no unit because it is just numbers. It can be 1, 2, 3, and etc. Exactly, it has no unit. Therefore, the unit of period is just the seconds. Is that clear? Good. And that's the mathematical expression. And the second one is the frequency. Frequency is just the number of revolutions an object undergoes every second. And mathematically, it is given as the number of revolution or oscillations, per unit time, or all over time taken. And that is F is equivalent to N all over T, where N has no unit because it is just the number of oscillations that you've made in each second. And the small t there is measured in seconds. So the SI unit of frequency is 1 all over seconds, which we call the hertz. Hertz, right? In bracket Hz. But you have to note that per second is the same as 1 hertz. 1 hertz is the same as 1 per second. Is that clear? Good. It can also be measured in revolution per minute. Clear? Good. Now we want to relate frequency and period. If you recall, I said the period is just the time taken all over the number of revolutions. And frequency is number of revolutions all over the time taken. So you've seen the pattern that I wanted to address here. You can easily notice that they're inverses of each other. If t is small t over n and f is n over t, we can simply say they are just opposite of each other. You know, we can also say that t is an inverse of f and f is also an inverse of t. Clear? Good. Can we make n the subject using t equals to t over n? So from here we will notice that Tn is equivalent to t, and small n will be T all over big T. Take note of that equation. Again, we have F equals to N over T, where N is equivalent to T over big T. Therefore, small f will be N, which is T all over big T divided by small t. So that gives us F equals to T over big T times 1 over T. So F will be, T will cancel T. So F equals to 1 over T. Is that understood? Let's see what F will be in terms of T. And from here, we can make T the subject. Also, F times T is equivalent to 1. Can we make T the subject? Yes, we divide everything by F. And that will be Ft is equivalent to 1. You divide both sides by F. F cancels, and this gives us T equals to 1 over F. This is why I said T and F are inverses of each other. Are inverses of each other. Good. Okay. Now let's derive an equation for the rotational velocity. We've dealt with the frequency and the time period. So let's talk about the rotational velocity. Rotational velocity, in bracket V. Good. Let's recall that from kinematics, V equals to S over T. But since we're dealing with rotational motion, we know that S will be 2 pi times r, that's the circumference of that circular part, and T will just be capital T. Is that clear? And this will be V is 2 pi times r all over big T. This is one equation. But then if T is 1 over F, then V can also be 2 pi r all over 1 over F. And this will be V equals to 2 pi r times F. And this is what we call the rotational velocity. Those are the two equations. Now let's answer this problem and see how it goes. It says a ball is swung in a circle. The frequency of the ball is doubled. By what factor does the period change? Let us write. We know T is 1 over F. That's the general equation. But here we are told that the frequency is 2 times the frequency, the initial frequency, right? So T1 will be equivalent to 1 all over 2 times F naught. So T is equivalent to 1 over 2 times 1 over F naught. So by what factor does the frequency change? Letter A says it remains the same. That is not true. The second one says it is cut to 1/2. Yeah, that is it. It is cut to 1/2 since they are inverses of each other. Okay. Viewers and listeners, thank you for following up my lesson. But then I'll come back to complete the remaining topics. And when next we meet, we will talk about the dynamics of UCM. And whenever we talk about dynamics, you know, forces are involved. So I will advise you to review your notes on dynamics, you know, and then you will enjoy whatever is to be presented next time. Till I come your way, have a nice day and be at home at all times in order to fight this deadly virus. Thank you so much for watching and listening.